Hello everyone. The topic of our work is 3D point cloud change detection for street scenes. With the rapid development of 3D acquisition devices, we are able to collect billions of points in a few hours. However, the analysis of the output data is a challenging task, especially in the field of 3D point cloud change detection. In this track, we want to explore efficient and effective techniques to detect the changes from multi-temporal point clouds in a complex street environment. Given the 3D LiDAR data from two different areas of the same place and the list of points of interest, we hope that participants can determine if there are changes and identify the change type. To achieve the goal, we provide a publicly available 3D change detection dataset. The dataset is provided by SHREC Media, and the data is acquired by a LiDAR scanner mounted on a moving car. We selected 78 street scene 3D point cloud pairs in the year of 2016 and 2020. With these large point clouds, we annotated 867 object pairs with 5 meaningful change labels. The labels are no change, removed, added, change, and color change. These annotated objects are given only change type and center location, and without any other information on the objects. There are two main challenges for our task. First is that few information on the objects are provided. Only center positions and the corresponding change labels are given in the training set, and in the test set we expect the participants to predict the change type of any location of interest. Another challenge is the data class imbalance problem. As summarized in Table 1, most data pairs are annotated as no change, and only 4% are annotated as color change, which means that if we try to use a learning-based method, it's very possible that we can only get a biased model, and it's really hard to detect the minority classes. Overall, 3 teams have contributed the work to this track. The first team proposed a 4-stage method based on hierarchical histograms. In the method, the first step is to extract object pairs within cylinders. Then we remove the floor of the extracted samplings and help us later to separate the different objects that may appear in the samplings. Then we estimate density clusters of each sapling in order to reject these objects that are far away from the center location, as they are not thematically related with the center object. In this step, we use an adaptive approach of the dbScan algorithm that separates the objects of the sapling into clusters based on the density. In the third step, we calculate the corresponding clusters of the objects of 2 different ears and estimate the mean accumulating distance of each point in one ear's clusters with the 15 closest points of the other ear's clusters. Creating in this way, we get a list of pairs and the corresponding distances. Then to easily compare the 2 ears' distances, we create 2 histograms. And with an equal number of bins, for example 15 bins. These histograms represent each one for the corresponding 2 clusters of each sapling. According to these histograms, we can only take into account the high values of the distances, assuming that they lie in the histograms between 40 to 15 bins, which can indicate what kind of geometric changes have happened. Finally, after the initial comparison for determining the geometric class of the object of interest, we take another step to find color changes between the point clouds and refine our classification. We convert the RGB information to HSV color space and use histograms to find color changes. The second team proposed a seminal network based on graph convolutional network and the inception network. Firstly, we extract the object pairs from large point clouds and remove plane surface and outliers. Then, to calculate the geometric changes between the two years point clouds, we perform a Hausdorff distance computing between each point in the 2016 object to its nearest neighbors in the 2020 point clouds and vice versa. We then perform thresholding to select the points with significant change in position. After the change computation, we build color change graphs and geometric change graphs. In the color change graph, calculation of the changes in color space is performed by first averaging the RGB values into respective red, green, and blue bins. A color space point cloud is generated by taking the average RGB values. The change in color space is calculated by applying a point-to-point Hausdorff distance. For each RGB point with significant change, its corresponding XYZ coordinate from the point cloud is taken. The KNN algorithm is used to generate a graph for color and geometric changes point clouds of 2016 and 2020 3D point clouds, respectively. The fourth point feature histograms are calculated for each point as the node features. The results from the three strings, the color change string, the point geometries from two different years, are then concatenated and passed to multi-layer perceptrons to generate the output. In the later thin scenarios where there are no points of significant change in both 2016 and 2020 point clouds, the object is directly labeled as no change. The third team proposed a seminal graph convolution network for 3D point cloud change detection. Unlike previous two methods, SAM-GCN can directly take the extracted point clouds as input without removing planes and outliers. Since the task is to classify change types instead of object classes, we don't need to extract the objects correctly. Considering that the point clouds are well registered, we extract the cylinders around the gap centers with an experimental distance of 3 meters for all samples. We don't expect the extracted point clouds have the same input point number, as our network is well designed to deal with this issue. And also, after object pairs are extracted from the large thin level point clouds, we apply a randomized oversampling metric to deal with imbalanced data. The general idea is to randomly duplicate samples in the minority class to make sure that samples of each class has the same probability being adopted in the training process. Then we adopt the edge condition, the graph convolution operator, as the backstop of our proposed SAM-GCN architecture. Edge convolution is adapted to dynamically update the edge features and have been proved to be effective in extracting powerful features from 3D point clouds. After that, we simply subtract the output vectors of the two branches and use 3 multiplayer perceptrons for final classification. The whole framework is quite simple and straightforward. As these 3 methods use quite different techniques, we evaluate them under the same overall accuracy and mean intersection over unit metrics. The quantitative results are summarized in Table 2. It's straightforward that the third method outperforms the other two methods on accuracy and IOU. The first method, as a non-learning based method, can achieve 60% overall accuracy and relatively balanced performance on all classes. The second algorithm, as one of the learning-based methods, achieves good results on classifying majority class low change, but fails on minority classes like change and color change. The third method has a very good overall performance on the dataset, especially on minority classes, which achieves over 95% accuracy on minority classes change and color change. However, on the majority class no change, the third method is not that effective. We draw conclusions from three different aspects. The first is handcrafted versus learning-based. From the quantitative results, we observe that the handcrafted algorithm can achieve relatively balanced results on overall and per class accuracy and MIOU, while learning-based methods have usually balanced output on different classes. But it's still obvious that learning-based methods can achieve overwhelming performance. So in the future work, we should focus more on how to improve the learning-based method to have balanced results on no matter majority classes or minority classes. The second aspect is on the class imbalance problem. Class imbalance has posed a challenge for learning-based modeling for a long time, as most machine learning algorithms are designed with the exception of an equal number of examples for each class. However, due to the limitations of data acquisition, class imbalance problem cannot be avoided. In your dataset, around 60% objects are labeled as no change and only 4% labeled as color change. Hence, it's important to deal with this problem. And the third method in your SHREC adopts randomized oversampling metric to avoid this problem and achieves good results on minority classes. This may help for us to designing a learning-based method for tasks on datasets with minority classes. The third aspect is about the network architecture. When adopting deep learning-based methods, we usually can design very different kinds of networks. In our task, there are two methods use the deep learning frameworks. The second one and the third one both adopt the graph convolution networks and use the seamless architecture. But they achieve very different results, and we compare these two networks and find that apart from the very different processing stage, we find that they use different operators to deal with the final output vectors. The third method adopts a subtraction operator, while the second method uses a concatenation operator. We invested the difference of these two different operators in the seamless GCM algorithm, and the results are summarized in Table 3, and we draw the conclusion that the subtraction operator is more effective and natural for our 3D change detection task. Hope that our work can contribute to the community of the 3D change detection. And if you have any questions, please feel free to ask me in the later Q&A session, and thank you.